Is Anirban Chatterjee and I'm from Walmart Global Tech, Bangalore, India. Today, I, along with my colleagues, will present our work. The title of our work is Detecting Concept Drift in the Presence of Sparsity, a case study of automated change risk assessment system. So this is the overview of our work. As part of this paper, we studied the effect of sparsity in detecting concept drift in data. So our primary contribution to this paper is as follows. Number one, provide an empirical guideline on applying data imputation given a data distribution and a sparsity pattern. Number two, suggest various metrics for concept drift detection. We found that some of these metrics in literature can be misleading in practice and propose some new ones that we found helpful. Number three, provide a majority voting based ensemble of concept drift detectors for abrupt and gradual drifts that perform well across the whole spectrum of concept drift detection metrics, a feat that individual concept drift detectors may not attain. Now let's briefly touch upon some of the preliminary concepts which this work is based on. The first thing that we would like to touch upon is sparsity. Sparsity or missingness will use these two terms interchangeably throughout this presentation. So missingness may be present in the data due to primarily two following reasons. One is data loss and another is faulty sensors. So data loss can happen in practice due to various ways. For example, your data is stored in distributed manner, and maybe one of the clusters where your data is stored has gone corrupted along with its backups. So that will eventually lead to data loss, and this kind of data loss will eventually lead to missing values in data. So another reasons could be faulty sensors. Suppose you have a lot of sensors installed at different places, and those sensors are continuously streaming values to some central data lake. And what will happen if some of those sensors start malfunctioning and stop streaming data to the central data lake? So then what will happen? Your data will suffer missingness or sparsity in with respect to some of its features. So these are some of the practical reasons missingness can occur in practice. There can be some other reasons as well, but these are the primary reasons. But what will happen if there is sparsity in data? So if the degree of sparsity is low, then it's not much of a problem to us, and we can simply ignore those data points which has at least one feature with missing values. But the problem arises when there is high degree of sparsity. For example, if there are many data points in our total data set, so which has at least one feature with missing values, then we can't simply ignore those data points which have features with missing values, because that will lead to heavy information loss. So what's the solution? The solution is to substitute those missing values with plausible values, or to put it in other words, we have to impute those missing values. But what's the problem of this imputation process? Because there are some standard imputation techniques which generally people use to impute missing values, but the problem arises because these imputation techniques are not 100% accurate, because these are all statistical techniques and this can't be 100% accurate. Now because of this lack of accuracy, what can happen is that after imputation, the observed distribution of the data will not be exactly same as the original distribution of the data. So there will be some shift between the original distribution and the observed distribution, and the amount of this shift will completely depend on the accuracy of the imputation techniques that we'll use. Now because of the shift between the original distribution and the observed distribution, so we may have some problems in detecting concept drift in data. Now before we jump into what is concept drift and how to detect that, let's also quickly touch upon various types of sparsity that we get to observe in data. So again, these are quite standard definition of sparsity. For example, MCAR, which is called missing completely at random. So according to this, missingness is unrelated to observed and unobserved features. Second type of missingness is called MAR, or missing at random. So here the missingness is related to observed features only. And there is one third type of missingness which we call MNAR, so which is called missing not at random. So here missingness is related to only unobserved features and possibly some of the observed features as well. Now, these are the various standard techniques to impute the missing values: mean imputation, median imputation, mode imputation, zero imputation, kth nearest neighbor imputation. These are the very standard techniques, plus there are some complex deep learning based techniques as well. So, I didn't mention all of them here. More or less, as the name suggests, that mean imputation means replacing all the missing values of a particular feature with the mean of the observed values. So similarly, we can do the same with median, mode, zero imputation as well. And I mean, we can if we replace the missing values with kth nearest neighbor of a particular feature, then we call it kth nearest neighbor imputation. Now I would like to hand it over to my colleague Shubhadeep, who is going to take you through the next section of this presentation.
Thank you, Anirban. Hello, everyone. My name is Subhadeep, and I will take you through the next portion of our presentation. So far, we have discussed about sparsity and missingness. Now, let us discuss about another important concept required for this work, and it is the concept drift. So, what is a concept drift? So concept drift is a phenomena where the statistical properties of the target variable changes over time. It basically means the relationship between the input and the target variable changes over time. Statistically speaking, we can define it as the change in the joint probability distribution of the input and target between two time points. Now, how does it affect our model? So the context has changed, but the model is not aware of the change. So when we train a model, we train it on static training data, and it has no idea of the relationship between the input and target variables are changing or not. It is completely unaware of it and as a result, so the prediction accuracy may decrease significantly in the presence of a drift. So what has to be done? We need to retrain the model. Now coming to the different types of drift, so there can be two types of concept drift. One is abrupt and the other is gradual. So as the name suggests, abrupt is kind of a sudden change over time, and gradual, in case of gradual, the change occurs gradually with time. So, for example, you can think of a price of a house which is dependent on, and we can take as the input the features of that house. But due to this COVID situation, which is ongoing now, the price of house has decreased significantly, and this is kind of a abrupt change. So the features of the house has not changed, but the price of house has changed, and it has occurred suddenly. Again, you can think of a cap price, which and for cap price is determined by the distance traveled by the passenger and the time of the travel. But the cap price may increase with the increase in the fuel price, and this is again kind of a gradual change, and this is an example of gradual drift. And so this is a pictorial representation of the two kinds of drift. So for abrupt, here you can see that at this point the mean of the target variable has changed suddenly and this. And for gradual, you can see the mean was here, and then there is kind of a fluctuation in this region, and after that the mean has changed fully. Now uh, let us discuss about concept drift detection. So for we have seen that concept drift is like a barrier to the successful application of machine learning model, and it needs to be addressed to ensure the model stays accurate and reliable. So we need to detect, monitor, as well as deal with concept drift. And as we discussed earlier, so we If we have a real world data, there could be sparsity, and we need to impute those missingness, and we will use this imputed data to train a predictive model. And once the model is trained, so the predicted outcomes are sent to the drift detector, and if the drift detector detects concept drift, then we need to retrain the model again on a new set of data. So now let's look into some existing works in concept drift detection. So first is ADWIN. So ADWIN stands for Adaptive Windowing, as proposed by Buffett et al. So ADWIN maintains two sub windows, one for historical data and the another is for new data. A significant amount of a significant difference between the means of these sub windows indicates concept drift. So the next is DDM. So DDM stands for drift detection method by Gamma et al. So this method detects concept drift in streams by analyzing the error rates and their standard deviation. So if the error rate increases, then DDM concludes that there is a concept drift. So next is EDDM, or the early drift detection method by Bena Garcia et al. So this method uses the distance between two consecutive errors rather than the error rate, as in DDM. So when the concept remains stationary, the distance grows larger, whereas there is a decrease in the distance. Then we conclude that there is a concept drift. Next, there is HDDM, which is Hovding's inequality based drift detection method by Blanco et al. So, as you can see, there are two variants of HDDM, which is the HDDM A and HDDM W. So, HDDM A uses moving averages method to detect drift, and HDDM W uses exponentially weighted moving averages. Now, KS-WIN is short for Kolmogorov-Smirnov windowing by Christoph et al. It maintains a sliding window of fixed size n, where the last R samples represent the latest concept. So Kolmogorov-Smirnov test, as you already know, that it is a test for equality of two distributions. Now a concept drift is detected if a case test between two distributions of R and n minus R samples yields a significant difference. Now is page Hinckley. So it signals concept drift when the difference between the observed values from the mean crosses over a user defined threshold. So now I will like to hand it over to my colleague Kunal. So he will take you through the next part of the presentation. Thank you.
Now let us take a look at the evaluation metrics. The most popular metric that you will find in concept drift detectors is frequential error. It is defined as the accumulated sum of loss functions. Another popular metric is accuracy, which is nothing but the overall accuracy of the prediction model. Let's see how these metrics will be determined for two detectors as shown in this example. Over here, the blue boxes denote the regions where the data is considered to be normal, and the red boxes indicate the drifts. Now let's say there are two detectors where the detector 1, as you can see, detects that there is a drift in 6 possible locations, out of which 3 it got correct and 3 it got wrong. On the other hand, there is a second detector which predicts only 4 drifts, out of which 3 has been correctly detected and 1 has been wrong. Now, if I were to ask you which one of these two detectors is probably the better for detecting concept drifts, it seems that detector 2 should be the winner, right? However, based on frequential error and accuracy, one would come to the wrong decision that detector 1 is in fact the better one. This happens because whenever a drift is detected, the model is retrained, and as a result, its frequential error goes down and its accuracy goes high up. And hence, one would say that detector 1 is better than the other, although it is not the case in reality. And the major point to note is that retrading is a costly process, and we should avoid it as much as possible. And consequently, one may be misled by looking into frequential error or accuracy alone. Hence, we propose four new metrics. The first one of them is the detection delay, which is the distance between the predicted and the actual drift. The next one is the true positive rate, which is the percentage of detected drifts which were true. Third is true positives per drift, which is the number of times a drift is detected. Note that ideally true positives per drift should be 1. That is, when a drift is detected only one, it should be detected only once. So for example, in this case, in the ideal scenario, a detector should have identified the drift in total 3 number of times. And drift count is the total number of true drifts that has been detected, which in other words, as per this example, means out of these 3 drifts, how many have one detector been able to identify. Now let's look into the problem. Now data imputation and concept drift detection has been studied separately. Now whether the data imputation with different sparsity level affects the concept drift detection, this thing has not been studied earlier. And that is what we are trying to address in this work. So what's the current strategy? The current strategy says that first find the feature distribution type and apply the imputation method according to the feature distribution. However, the a problem may arise in case the features are actually related. So how can we solve it? The solution is use the known data. So this is the method that we propose. That the first there is the original data, which as you can see over here has some missing values. Now what we'll do is we'll pick up only those rows where there is no missing data, and as a result we are left with these 4 rows as shown in figure B. Now what we do is we introduce sparsity, and we introduce sparsity into those features which have had sparsity in the beginning, and the sparsity level is also determined by the actual sparsity level that was present in the original data. Now note that we know that the ground truths for these rows, and as a result we can find the best data imputation scheme using RMSE metric, and then upon finding the best data imputation scheme we apply it on the original data and try to predict the missing values.
Well, so let me begin with experiment. So first we'll describe how we have started with synthetic data and what method we have followed to identify the best imputation technique. So we take a synthetic data having multiple feature and we introduce sparsity in the data systematically. Later we impute missing values using mean, median, zero, mode and KNN techniques. After that we have checked RMSE value for each of this imputation technique, and whichever has got lowest RMSE has appeared as winner. So in the table you can see uh, for normal distribution, uniformly distributed data and chi-square along all sort of all sort of missingness, mean appear as a winner. But when data follows Cauchy distribution or binomial, median appear as winner. Also, for normally distributed data, median performs more or less similar to mean, and for when data is generated from Cauchy distribution, zero imputation performs reasonably well. When data is multivariate normal, for missing completely at random and having less than 30% missing data, KNN with 15 errors appears as winner. Whereas when the nature of missingness increases, number of missing percentage of missingness increases, we have to increase the number of nearest neighbors, and that holds for other two techniques as well. Next we have performed the same experiment with Harvard Dataverse,
So, as this data real world data set has dependencies among features, so along with these traditional methods, we have used some of the uh, sophisticated techniques as well. For example, there is a technique called iterative imputer, which consider each feature having missing value as a function of all other features, and it repeats the process over and over again, and intermediary values of missing feature is used to predict the value for other missing features. Correct. Another technique is called soft impute, which is actually a matrix completion techniques. It internally uses low rank singular value decomposition. Uh, Synchron with optimal transport is also been tested. So it actually leverages the distance, optimal transport distance, by turning it into a loss function to impute missing value. Here in the table you can see for Harvard data bars, when data is normal, distributed or uniform of chi-square, for normal and uniform, synchrons with OT, that means optimal transport, appear as winner. For chi-square binomial, median performs well for MCAR and MAR, but when data is, missingness is missing not at random, that means that follows a pattern, then mean appear as winner, right? For chi-square, for binomial it is mean or median. For multivariate normal, we can see that iterative or OT appear as winner. For log normal, synchrons with OT, that means optimal transport, wins, right? Next, we apply QQ plot to check the similarity with different distribution, right? When theoretical, so QQ test actually checks distribution between two, similarity between two distribution. So whichever among which these 5 plots, whichever comes more closer to 45-degree line, that appear that appear as the most similar one, right? So here we can see that chi-square is the most similar one in compared to other distributions, right? So we can choose chi-square here as a winner. Okay, next, one might ask that when we are checking with when we are performing concept drift, right? We are trying to identify concept drift. Is there any need for imputation, or it's not at all required? So we have performed this experiment for all dataset. Just we are presenting result with one dataset for ease of understanding. You can see that along all metric, that means frequential error or accuracy or average detection delay or true positive rate or true positive per drift or drift count, for all drift detection algorithm, when you are not performing any imputation, that result is performing imputation actually improves the result, even if sometimes small, but it improves the result overall, right? So that clearly indicates that we should impute the data, then only concept needs to be checked, right? Without imputation, the model's performance might degrade, right? So there is this indicates that there is a need for checking. There's a need for imputation, and then you can perform your experiment concept drift detection algorithms. Well, this part is quite interesting. So here we are choosing, we are trying to choose the winner among all this algorithm, right? So just see this, see the plot for frequential error, right? The lower the value of frequential error is, it is more acceptable, right? So you can see that EDDM performs best here, correct? If we check frequential error, if we go with accuracy, this also holds true, right? With up to 20% missingness in data, right? Accuracy is best for EDDM, but it takes quite a lot of time to detect the the drift, right? So average detection delay is quite high. That means even though it is best if we check frequential error and accuracy, but iridium is not best in terms of average detection delay or true positive per drift, because ideally true positive per drift should be 1, right? For a drift it should detect it just once, right? So you can see that iridium though performs best when frequential error and accuracy is considered, but its performance degrades when, I mean, it is not a winner if we check average detection delay or true positive per drift, right? Same holds for other techniques as well, right? It appears that there is no clear cut winner, right? And if we check ensemble, that even is not always the winner, but it appears as the second best one. So instead of choosing any of this algorithm, it's better to stick with ensembling this weighted ensembling of this different techniques, correct? Same trend you can see for, so this one is for Harvard dataverse with abrupt drift. Same trend you can see when concept drift is gradual, right? So here what I am trying to indicate is that what I am trying to present is that none of this algorithm appears as clear cut winner. So let's go with majority voting, right? That means ensembling of these techniques. Well, what is our finding here? So as you can see that concept drift actually in presence of sparsity poses a major challenge in machine learning algorithm, right? And none of this known algorithm is actually clear cut winner. So we go with majority voting, correct? Yeah, that ends our presentation. Thanks for your patience.